The Webb glance is such a long way out that it's catching light that has been voyaging for over 13 billion years. Yet, the universe has been expanding, and thus the light has been stretching. For the most distant worlds, we're looking back in time nearly to the Big Bang. The immensity of the universe might seem vast, but every last bit of it started from what we refer to as the singularity. As of now, this is our understanding of the Big Bang theory. The James Webb Space Telescope, JWST, has revealed significant mysteries about the birth and development of the universe, leaving us dumbfounded. Prestigious physicist Brian Cox has proclaimed that the remarkable discoveries made by the JWST might actually reshape our understanding of the universe as a whole. Join us as we dive into these new heavenly discoveries that promise to change our comprehension. The James Webb Space Telescope, named after the distinguished NASA administrator James E. Webb, stands as a marvel of modern astronomical exploration. This telescope represents a significant technological leap forward from its predecessor, the Hubble Space Telescope. Resulting from a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency, the JWST surpasses the capabilities of its predecessor. It utilizes cutting-edge technology and a design optimized for studying the universe in unprecedented detail. Unlike Hubble, the JWST delivers clear and sharp images of distant celestial bodies, working primarily in the infrared range. This remarkable feature allows it to penetrate cosmic dust and capture celestial objects that were previously hidden from view. With its giant 6.5-meter primary mirror made up of 18 hexagonal segments, the JWST dwarfs Hubble's reflector size. Positioned roughly 1.5 million kilometers away from Earth at the second Lagrange point, L2, it orbits the Sun in sync with Earth, ensuring a stable and uninterrupted view of the cosmos. Observing light that has traveled for billions of years also means engaging in a form of time travel. The JWST uses infrared instruments to observe celestial objects and events dating back billions of years. Because of the expanding universe, light emitted by these objects undergoes redshift shifting from the visible spectrum to the infrared. Fortunately, the JWST can detect this redshifted light from incredibly distant bodies, enabling scientists to study the birth of stars, explore galaxy formation, and analyze exoplanet atmospheres. Its most recent historic discovery involves identifying an enormous mass of galaxies at the edge of the observable universe. This finding challenges the current theory of cosmic formation, prompting a reassessment of fundamental cosmological assumptions. To better understand how we arrived at this point, let's take a brief journey through the history of space exploration. Early civilizations, such as the Greeks and Chinese, laid the foundation for understanding planetary motion by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the mid-20th century, Edwin Hubble, a pioneering astronomer, made groundbreaking contributions to cosmology and observational astronomy. His work revealed that distant nebulae were, in fact, separate galaxies far beyond the Milky Way, altering our understanding of the universe's scale and expansion. Hubble's law showed that galaxies farther away were receding at faster speeds, offering solid evidence of the universe's expansion. The post-World War II era marked the start of the space race, with milestones like the Soviet Union Sputnik in 1957, Yuri Gagarin's orbital flight in 1961, and the Apollo 11 moon landing in 1969. Fast forward to 1990, the launch of the Hubble Space Telescope provided unparalleled clarity and insight into the universe. From ancient sky watchers to the technological marvels of the James Webb Space Telescope, our exploration has constantly evolved. Hubble captured iconic images like the pillars of creation in the Eagle Nebula, revealing stellar nurseries within columns of gas and dust. It also produced the Hubble Deep Field, exposing thousands of galaxies in a seemingly empty patch of sky. Hubble explored exoplanet atmospheres, detecting elements like water and organic molecules, hinting at possible habitable zones beyond our solar system. Its observations of supernova SN 1987A illuminated the life cycles of massive stars, cementing its legacy in modern cosmology. The JWST was launched to build on these technological advancements and lessons. According to the prevailing theory, the universe began around 13.8 billion years ago from a hot, dense singularity that expanded rapidly, creating matter, energy, and fundamental forces. As it cooled, atoms, stars, galaxies, and cosmic structures began to form. The Big Bang theory also explains the cosmic microwave background radiation, the abundance of light elements, and the large-scale structure of the cosmos. Despite its wide acceptance today, the Big Bang theory initially faced skepticism. Alternatives like the steady-state model proposed a universe without a beginning, and some questioned the evidence for an expanding singularity. These doubts were largely addressed, especially after the 1965 discovery of cosmic microwave background radiation, a key prediction of the Big Bang. Space missions like COBE and WMAP further reinforced the theory. Enter the James Webb Space Telescope. Equipped with advanced infrared instruments, it peers through cosmic dust and captures the oldest light in the universe. Its ability to study cooler objects, such as exoplanets and brown dwarfs, and its focus on star-forming regions hidden from optical telescopes make it ideal for studying the early universe. As celestial bodies move away, their emitted light stretches, a phenomenon known as redshift. The JWST's infrared capabilities allow it to detect these redshifted signals, offering profound insights into the universe's origins and evolution. High-energy events like black hole mergers or starbirths often emit in the infrared, expanding the JWST's research potential. It complements telescopes like Hubble with enhanced sensitivity and the power to detect faint, distant objects. Recently, JWST observations uncovered enormous masses of galaxies near the edge of the observable universe, galaxies that existed mere hundreds of millions of years after the Big Bang, during the cosmic dawn. What puzzles scientists is how such vast structures formed so early. This could lead to a fundamental reassessment of how galaxies formed and evolved in the early universe. These observations raise big questions about the composition, structure, and governing forces of the cosmos. Hubble was revolutionary, but its reliance on visible and ultraviolet light limited its view of the early universe, as these wavelengths are absorbed or scattered by dust and gas. The JWST, with its infrared sensitivity, now enables us to see celestial objects that formed shortly after the Big Bang. Its observations reveal an unexpectedly high number of early galaxies, suggesting the universe may have evolved faster and more intricately than previously believed. Some early galaxies appear too well developed for their age, challenging models that predicted slower growth. These findings hint at a denser, more complex cosmic web than we imagined. The presence of such massive structures challenges our assumptions about cosmic evolution. Scientists must refine current models to account for how these galaxies formed without violating core cosmological principles. The JWST also revealed unexpected conditions in the early universe, variations that suggest previously unknown physics or phenomena. Initial observations, while exciting, often differ from deeper investigations. For example, galaxies once thought to contain only light elements like hydrogen and helium have now shown heavier elements through spectroscopic analysis. This challenges long-held ideas about the early universe's chemical makeup and the processes responsible for dispersing elements across space. Likewise, early assumptions about a uniform pattern of galactic development have given way to evidence of complex, diverse chemical compositions among early galaxies. In conclusion, the cosmos is a vast, intricate puzzle. While initial glimpses can be awe-inspiring, thorough and careful investigation is essential to truly understand the universe. Techniques like spectroscopy, analyzing light to determine the properties of celestial objects, are invaluable. They help us decode the origins, composition, and movements of stars and galaxies.